Hello and welcome back to this course on fundamentals of data science. And now we are discussing about the regression model. We talked about what is a simple linear regression, and today we are going to estimate how this regression model can be evaluated. In other words, what are some of the evaluation metrics. Basically, we are going to look into this R square and adjusted R square. These are two different methods. Of course, there are different methods available, but we are just going to focus on these two methods that are available. So that's our objective for today's discussion. We know that basically, as far as regression is concerned, the main objective is to predict the value for y for a given x. So that's the prediction model, and when you predict such models, when it is appropriate for us to go for regression, and how good is our prediction. So that's another question that we have to answer. And at times regression can also be used for predicting continuous values by learning various dependent or independent, various independent features. For example, predicting price of a house based on features like number of bedrooms, number of like living rooms or bathrooms that's in the house, along with the locality where the house is located. It's some of the features. And at times it can also be used for classification. So let's go directly into this regression model. We will just recap what we have seen so far. We know that basic classification or regression works in simple ways. We determine whether the independent variable explain a significant variation in dependent variable. In other words, whether a relationship exists. If there is no relationship exists, in other words, if there is no correlation between these two variables, then it's not easy for us to catch up with the regression model. And we also have to determine how much of the variation in dependent variable can be explained by the independent variable. In other words, the strength of the relationship. Finally, they determine the structure or form of relationship, like mathematical equation relating to independent variables and dependent variables. Again, just for your reference, the independent variables are the x values and dependent variables are the y values. Suppose we have x and y, where x is the independent variables and y is the dependent variables. We always keen on predicting the dependent variables. The y is what we are going to predict. So that's the basis that we have. So we start from some initial configuration of the model and predict the output based on some input that we have in hand. And also we predict the value by comparing certain target measures that we have in hand. For example, here is a simple line. Consider this as the regression line that you have in hand. And for regression line, this is the actual line or predicting line, you can call it as. And these blue points that we have here, these blue points are the observed points. So we should think about this variation that we have between the actual model, and is there any way that we can adjust such things? So we are going to discuss about those points in today's discussion. So we know that the regression task in itself is kind of prediction of a state of outcome for a particular variable, in this case the dependent variables. And we are going to see, is there any close correlation between the independent variables and the dependent variables. Though at times regression can also be used for classification, which we will consider later on. But for the time being, let's see what are the basic methods that are available for evaluating such regression models. So when it comes to the regression evaluation, the validation process can involve analyzing the goodness to the fit. So you may have a spread of data points which are distributed along the x and y axis. Let's say you have such data points there. So you want to analyze the goodness of fit of the regression line. How good the regression line fits all the data points, and analyze whether the regression residuals are random, and checking whether the model's predictive performance deteriorates substantially when applied to data that were not used in model estimate. Anyway, we cannot have a perfect regression model, but we can find a best fit which has less error or less residue. So you can see in this case all the red points that we saw here, that we see here, are the actual values, or in other words they are the observed values, and this line that we drawn is the actual predicted value. So we do see a difference between the actual value and the predicted value. So there is this difference we call it as the residual or the error. So this is only one line that I have drawn. Probably there might be another regression line that might go like this. For example, we are not sure, like maybe this line is having better fit than the previous one, but we have to calculate. For example, like suppose this point is, say, the actual value is y, and this is the y bar. Say we have taken this, so it's like y1 minus y1 bar plus y2 minus y2 bar. So for each and every points you have to take the values. So let's say this is y3 bar, y4 bar. For each and every point you have to take this and sum up the entire thing, and finally you will come up with a value, and see which of the lines have least value. The line which has least value is a best model that fits. Yes, here one measure of goodness of fit is, we call it as R square. R square is a kind of goodness of fit model. So which an ordinary least square with a intercept range between 0 and 1. That's what we have. And as far as this R square is concerned, so R square close to 1 does not guarantee that a model fits the data well, and R square can occur in the presence of misspecifications of a functional form of relationship, or the presence of outlier that distort the true relationship. At times you do have some outliers. Says if a data point is somewhere here, it really is an outlier, and that can actually distort the true relationship that can be observed. Okay, with this thought, let's look at another time. Let's look at another example here. This simple example also is for the linear regression model. We have x and y given to us, and we have to find the regression line equation. Also we have to estimate the error. So if you want, you can also plot and check it out, because it's very simple. Data is given to us with x as 1, 2, 3, 4, 5 and y as 2, 4, 5, 5, 5, 4, 5. Well, we are calculating this simple form. You can either go by this method. This is in fact is similar to, you can say, y equals beta naught plus beta 1 times x. The same can be represented, where beta naught is your y intercept, and yeah, beta 1 is your regression coefficient or the slope of the line. Same equation of the straight line can be expounded into this regression model, and you can calculate these values with the tables and just try to find the regression equation from the given data. So we just calculate by each step. We are trying to observe the points for x square x times y and calculate the value of m, in this case the slope, that is nothing but the beta 1. The regression equation is similar to the equation that we have for the straight line with a slope, and we do find the y intercept, that is beta naught, and finally you come up with this regression equations. Yes, with this regression equation you can actually predict the values for y for any given x input. So that's the objective of this model. So now with this model we can check what is going to be its evaluation metrics. Okay, we are trying to find the error now. That is where we are going to see how much error we have. So in order to find the error, we have to estimate values for estimated y and also the actual y. So for estimated y and the actual y's, we are going to take these values and you are going to subtract the value, and then when you take up the root you get the actual values. In fact, you can also see here we are summing up all the values, summing up all the estimated value minus the actual value, the whole power 2, so that we make sure there is no negative values coming up there, and then eventually you are taking the roots again. So that's one way to find the actual error for a given line. So with respect to the R square, so the better linear regression, as you can see here, this line fits the data in comparison to the simple average. So actually we are talking about these two things here. If you look closer, the values of R square is 1. So the areas of the blue square here represents the square residual with respect to the linear equation. The areas of red square here, as we can see here, represents the square residual with respect to average values. So blue squares are here, represent the square residual with respect to linear regression. And generally speaking, this one on this particular part, it shows the data points are there, and data points are all being connected, but in between the data points, the blue shaded ones are the actual residuals that you have here. These are the residuals. Okay, let's talk more about this R square then. So R square, as far as R square is concerned, we always have to determine this coefficient. R square is, as you can see, 1 minus the sum of residual by sum of the total residuals. So this can also be written in different forms. At times people also write R square as 1 minus the mean square error by the mean square error of the model by baseline. So different evaluation metrics. Here is the basic thought of R square model. Just imagine here is the spread of data. You are given with the data points, and your x-axis is your experience and y-axis is your salary. Suppose now we are going to have a line, and this line we have drawn from the mean value. You have taken the mean value, and from the mean value you have drawn this line with respect to y. So now this is the mean of y. For the mean of y you have drawn this line. The yellow line is the mean of y, and now we are trying to find the difference between this yellow line and other data points, and you are going to sum up or take the summation of all the data points. So that's what it's been stated here. These two things, the y average, the yi minus the y average, the whole square, that's one huge sum. The other one is y minus y1 the whole square, the residual sum. So you are taking these two values, summing up together, and then you are subtracting with 1. So you can always see what happens at this point of time. What happens if, of course, the y average cannot be 0. That's one thing you can observe there. And if suppose it does becomes 0, what happens? Or what happens if the the residual value is 0? Yeah, of course we know that the different models or different forms of regression lines can be formed. Of course, the best fit line should have residual of 0. So we have seen here the better regression lines fits the data in comparison to the simple average. So always we want a better regression line that fits the whole data points, so that the closer R square will be to 1. So once this term becomes 0, R square will be just 1, right? Yeah, but one problem with R square as a measure of model validity is that it can always be increased by adding more variables into the model, except in the unlike event that the additional variables are exactly uncorrelated with the dependent variables in the data that is being used. So the coefficient of determination of R square is one of the basic metrics used for evaluating the performance of the regression model. So this particular metrics for evaluation help us to compare our current model with a constant baseline model. And what is it telling? It tells us how much our model is better. That's the basic thought that you have here. And as we have seen, they do have some limitation with respect to adding more variables to it. So that's where the adjusted R square comes in. When it comes to adjusted R square, we can add some values or variables. For example, the base value is say B0 in the example that we have seen for regression line with respect to experience and salary. X and Y. So you can add up more variables to it. For example, beta naught is we are starting at here. For example, this is your 20K, 40K, 60K. That's going to be your beta naught, and you are telling like maybe some years of experience with some special skill set and age. There may be many factors that can be included as beta 1, beta 2, beta 3, and so on and so forth. So basically that's where we started with respect to r square, and we can adjust this actual r square in a different forms. So this adjusted r square is of this form 1 minus r square times n minus 1 by n minus p minus 1, where p is the number of regressor and n is the sample size. So we always strive to make sure that this residual becomes 0. If that is 0 or should be very as less as possible, your system is quite good. And the same thing is true here again, like we talked about r square, this residual. If the residual is 0, then our fit is almost perfect fit that we have. So another question is r square can be negative? What do you think? So there may be some evaluation metrics to show the reasons why r square at times be negative, and one of the main reasons that r square be negative is that the chosen model does not follow the trend of data causing r square to be negative. So for example, if you choose a numerator model, and if you have this whole process of r square equals 1 minus residual by, this is what we have, and you can imagine like what makes this negative is that if this whole structure or residual by the average is greater than 1, then you can expect this whole model can be the negative, which means the numerator should be greater and your denominator should be less. So that's a very tricky model. As you can see, the actual trend in which the data distribution appears will be quite different when it's appearing to be a negative one. That we have to be careful with. So this is what we have here, and with respect to various analysis model for this one, we have MSC is the mean square error is one of the evaluation metrics for the regression, and then the root mean square error is another one, and we talked about the r square. R square is also called the coefficient of determination, and finally we had the adjusted r square. So these are different methods that have been used for evaluation process, and with respect to this there are different ways with respect to their formula, and some of the formulas are quite simple. As you can see here for MSC, it's just we are just subtracting the y minus y bar. The thing here is the square of difference between actual and predicted. This is actually the square of difference between the actual and predicted model we are taking it. And as far as the root mean square is concerned, it's quite simple. We are just going to take a root and we have the predicted value minus the actual value, the whole square by n. It's another model. If you wish, you can actually go for all 4 evaluation metrics and compare these evaluation metrics and see which evaluation metrics fits your data points well. Yes, there are different ways in which you can actually evaluate the regression process. We know that regression is one of the basic machine learning methods which is used for prediction, of data, and at times it can also be used for classification. But as far as this prediction is concerned, based on this 4 evaluation metrics, you can actually come up with which evaluation matrix is better. And moreover, as we have seen, for example, R square or some of these metrics have its own limitations. So at times it doesn't fit, or at times it doesn't really provide all that are needed for our evaluation process. And there is another problem with respect to evaluation process. Sometimes our data spread is so diverse, and if you like to fit all the data points, maybe we always have some struggle. We know that this straight line approximately represents all the data, but what if I want to fit all the data points like this? Well, I would call this as the so-called overfitting. Well, if you have such models like this model seems to have less residue, right? Almost the residue is 0. In other words, the error is 0. You feel that in the first instance, you feel that this kind of model is really great because you don't have any error, it fits all the data points. But in reality, if you want to represent this model, this becomes a huge quadratic, not only quadratic, it will be of multiple variables with multi-polynomial regression. When it comes to that polynomial regression, they becomes more complex. Sometimes some of the features are not needed actually. When we talk about house, for example, if you have y equals beta naught plus beta 1 times x plus beta 2 plus x, say we have x1, x2, beta 3, say x3, beta 4, x4, say 1. So as the power increases and the polynomial values increases, the number of features increases, the system becomes more complex as a whole for us to represent and to evaluate the system. So we need to understand this, and we want to try to reduce the number of features as much as possible so that our system becomes more simpler. So at times we don't want to fit the whole data, and this is one of the problem in many machine learning models, that at times it goes on to overfit the model. So we should be careful, we don't want to overfit and fall into such troubles. Okay, this actually leads us to next issue. So I just told you that when you have data spreads like this, for example, you don't have to say this, like we don't have to fit it like this, you don't have to do that. Yes, so for that we actually have another form of regression, we call it as logistic regression. So we are going to look at in detail about this logistic regression in our next lecture. So I will skip this for the time being so that we can have time to discuss about this particular regression model in our next lecture. So what did we see today is about the regression evaluation methods. Basically we focused on the R square and adjusted R square. Of course there are other methods like mean square error and root mean square error, and also at times we also have one simple model is called mean absolute error. Which is very similar to the mean square error, as you can see here, but we take the absolute values. Instead of square, we just take the absolute values. So where y is the actual or observed values, and this is the predicted value, and we are just taking the absolute. As you can see, this is the absolute sign, absolute value, so that there is no negative value comes out. So it's another methods. All these methods can help us to understand how well the regression line fits the whole data that are given there. Well, we'll stop here and we'll going to discuss about regression type, different types of regression, including the logistic regression and its explanation in the next lecture. I am looking forward to see you there. Until then, goodbye.